More than 2,000 kilometers wide, hidden entirely on the far side of the moon, invisible to anyone standing on Earth and looking up, sits the largest, oldest scar in our entire solar system. For decades, scientists knew it was there, and knew it was old, but couldn't agree on exactly what created it, what direction it came from, or what it had actually done to the moon's interior when it hit. In June of 2026, 2 companion studies built specifically to prepare for NASA's return to the lunar surface finally answered those questions, and in doing so, revealed something genuinely remarkable. Pieces of the moon's deep interior, material that formed when the moon itself was still a ball of molten rock billions of years ago, sitting scattered across the surface, in exactly the region where NASA's Artemis astronauts are now planning to land. This is the story of the South Pole Aitken Basin, the ancient impact that carved it out of the moon's far side, and why the scientific groundwork being laid for the Artemis program has just revealed something astronauts may soon be able to walk on and pick up with their own hands. Rock from the moon's deep interior, exposed by a collision so violent it happened before nearly anything else we can still see on the lunar surface today. To understand why this discovery matters so much and why it's directly tied to where NASA is now planning to send its next generation of astronauts, you first need to understand what the South Pole Aitken Basin actually is and why scientists have spent decades trying to understand exactly how it formed. The South Pole Aitken Basin, often shortened by researchers to simply SPA, is a massive impact structure sitting on the far side of the moon, the hemisphere that never faces Earth. At more than 2,000 kilometers across, it's not just the largest impact basin on the moon. According to researchers at the Southwest Research Institute, it's the largest confirmed impact structure found anywhere in the entire solar system, larger than any crater identified on Mars, Mercury, or any other rocky body we've been able to study in detail. It's also, by a considerable margin, one of the oldest surviving features on the moon's surface, having formed sometime during the earliest chapters of the moon's history, likely within the first several hundred million years after the moon itself came together. That combination, extreme size and extreme age, is exactly why the basin has become such a valuable target for lunar scientists. Newer impacts and volcanic activity have reshaped and resurfaced large portions of the moon over the following billions of years, gradually erasing much of the direct physical evidence of what the moon's earliest history actually looked like. The South Pole Aitken Basin, because of its sheer scale, has largely survived that long process of resurfacing relatively intact, preserving a kind of direct physical record of an extraordinarily early violent chapter of solar system history that's been erased almost everywhere else. As Dr. William Bottke, director of the Center for Lunar Origin and Evolution at the Southwest Research Institute, put it directly in a statement accompanying the new research, the basin offers scientists a rare opportunity to study the moon's earliest history, a record that exists almost nowhere else in this kind of preserved, accessible form. Despite that scientific importance, and despite decades of study using orbital spacecraft, researchers had never fully agreed on the precise details of how the basin actually formed. The structure has always looked slightly unusual, stretched and tapered in a way that didn't quite match the roughly circular shape typically produced by a straightforward head-on impact, hinting that whatever object created it must have struck the moon in a more complex, angled fashion, rather than hitting the surface dead-on. That's exactly the specific question the 2 new companion studies, published in June of 2026, finally set out to resolve, using a combination of detailed computer simulations and careful analysis of existing NASA spacecraft data. The first study, published in the journal Science Advances and led by researcher Shigeru Wakita, alongside 10 colleagues including Bottke, focused specifically on modeling the physics of the original impact. Itself, testing different combinations of impact angle, speed, and direction against the basin's actual, observed shape to determine which specific combination could plausibly reproduce that unusual, elongated structure. The second complementary study, published in the Journal of Geophysical Research, Planets, and led by researcher Gabe Gauman alongside Bottke and several other collaborators, took a different but directly related approach, analyzing detailed gravity data gathered by NASA's Gravity Recovery. An interior laboratory mission, known as GRAIL, combined with topographic measurements from the Lunar Reconnaissance Orbiter's laser altimeter instrument to map out the specific structure and composition of the material blasted outward from the basin during that original impact, material scientists refer to as ejecta. Together, according to reporting on the findings, these 2 studies concluded that the object responsible for creating the South Pole Aitken Basin approached from the north and struck moving southward, hitting the lunar surface at a relatively shallow angle of roughly 30 degrees from horizontal, rather than coming straight down and moving at a speed of approximately 13 kilometers per second at the moment of impact. That specific combination, a large object arriving at a shallow, glancing angle rather than a direct head-on collision, helps explain the basin's unusual, stretched, tapered shape, a detail that had puzzled researchers working with less detailed data for years beforehand. But the angle and direction of the original impact, while scientifically significant on their own, aren't really the most striking part of what these studies revealed. The more significant finding involves exactly what that specific kind of impact would have done to the moon's interior at the moment of collision, and what physical evidence of that process might still be sitting on the surface today, waiting to be studied directly. According to Buck's own description of the findings, the collision struck the lunar surface with such tremendous force that it may have excavated material from deep inside the moon, including portions of the lunar mantle, the thick layer of rock that sits beneath the moon's outer crust, material that, under ordinary circumstances, remains buried far too deep to ever be directly accessed or studied from the surface. The Gumman-led gravity mapping study specifically identified regions within the basin's ejecta, the material blasted outward and scattered across the surrounding surface during the original impact, that appear to be made of exactly this kind of mantle-derived material, rather than the more typical crustal rock that makes up the vast majority of the moon's visible surface elsewhere. That's a genuinely remarkable finding, and it's worth taking a moment to appreciate exactly why. Under normal circumstances, studying a planet or moon's deep interior directly is essentially impossible. Nobody can simply dig down through dozens or hundreds of kilometers of solid rock to physically sample material from that depth. Scientists studying planetary interiors are almost always forced to rely on indirect methods instead, things like seismic measurements, gravity data, or careful modeling, to make educated inferences about what a planet's interior is likely made of, without ever directly handling a physical sample of that material. An impact violent enough to excavate genuine mantle material and scatter it across the surface represents something considerably rarer and more valuable. A natural, if extraordinarily violent, shortcut, one, that brings deep interior material directly up to a surface where it can, at least in principle, be physically collected, studied, and analyzed using the same kinds of laboratory techniques scientists would otherwise never be able to apply to material from that depth. This connects directly to a separate, related piece of research published just months earlier, in October of 2025, in the journal Nature. That study, examining the shape, topography, crustal thickness, and surface composition of the South Pole Aitken Basin in detail, identified something specifically tied to the moon's very earliest history. Evidence that thorium-rich magma ocean liquids, material, scientists refer to using the acronym CREEP, standing for potassium, rare earth elements, and phosphorus, persisted specifically beneath the southwestern portion of the basin at the exact moment the ancient impact occurred. That finding connects to one of the broader foundational theories in lunar science. The idea that the moon, in its earliest history, was likely covered by a vast, planet-wide ocean of molten rock, which gradually cooled and solidified over time, with certain specific chemical elements becoming concentrated into a thin, final layer as that global magma ocean finished crystallizing. Finding direct physical evidence of that ancient, thorium-rich final layer, preserved specifically beneath one portion of the South Pole Aitken Basin at the moment of impact, offers scientists a genuinely rare, direct window into the tail end of that extraordinarily early period of lunar history, one that current theoretical models had described only indirectly through calculation and inference until this kind of direct physical evidence became available. Here's where this entire body of research connects directly and specifically to NASA's Artemis program, and why it's genuinely accurate to describe this as knowledge NASA's broader Artemis effort is actively uncovering, even though the specific studies involved robotic spacecraft data and computer modeling rather than astronauts physically standing on the surface. NASA has selected the lunar South Pole, much of which sits within or immediately adjacent to the South Pole Aitken Basin itself, as the target region for its Artemis crewed lunar landings, driven primarily by two key factors: the presence of water ice, believed to be trapped within permanently shadowed craters in this region, and the availability of long, sustained periods of sunlight at certain nearby elevated locations, both considered essential resources for establishing any kind of sustained, long-term human presence on the lunar surface. According to detailed reporting on the specific proposed Artemis landing sites, several of the leading candidate locations, including sites named Noble Rim 1, Noble Rim 2, and Hayworth, sit directly within the South Pole Aitken Basin itself, while additional candidate sites, including Malapert Massif, sit near the basin's rim, and De Gerlache Rim 2 sits just outside its boundary. That overlap means the mantle-derived material identified in this new research isn't sitting in some remote, difficult-to-reach part of the moon that astronauts will never actually visit. It's potentially sitting directly within, or very close to, the exact same handful of candidate landing sites NASA has already identified as the leading targets for its crewed Artemis missions. As Butke put it directly in the research team's own published statement, the combination of impact and gravity modeling gives scientists a powerful roadmap, one that tells them not just how the South Pole Aitken Basin actually formed, but specifically where to look for the rocks that can help answer some of the biggest remaining questions about the moon's origin and evolution. Questions that have remained open for as long as humans have been sending spacecraft to study the moon in detail. It's worth being precise and fully honest about exactly where NASA's Artemis program currently stands, since that context matters for understanding exactly what this discovery represents right now, rather than at some point in the future. As of 2026, NASA has not yet landed astronauts on the lunar surface as part of the Artemis program. Artemis II, a crewed mission carrying astronauts Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen, launched successfully as a flyby mission, sending the crew on a journey around the moon without actually landing, serving as a critical test of the Space Launch System rocket and Orion spacecraft in preparation for an eventual crewed landing to follow. During that same flyby, the Artemis II crew studied the moon's Oriental Basin, a separate, though similarly ancient, impact structure, using gravity data gathered by the earlier robotic Grail mission, demonstrating the same kind of combined orbital data plus crew observation approach that's expected to eventually apply to the South Pole Aitken Basin as well, once astronauts are actually able to land nearby. Artemis III, the mission specifically planned to finally return astronauts to the lunar surface, remains targeted for a landing near the South Pole, using NASA's Space Launch System and Orion spacecraft, combined with a lunar lander built by SpaceX based on its Starship vehicle. That mission has faced repeated schedule delays, and as of the most recent reporting available in 2026, a firm, confirmed landing date remains somewhat uncertain, part of a broader pattern of technical challenges that have affected the program's timeline as NASA works through the genuinely difficult engineering challenges involved in safely landing and later launching astronauts from the lunar surface for the first time in over 50 years. That timeline uncertainty doesn't diminish the significance of what this newer research has actually accomplished. Rather than representing something astronauts have already physically found and brought back, this research represents something arguably just as valuable at this particular stage of the program: a detailed, carefully modeled roadmap built specifically using existing NASA orbital data that tells mission planners and future astronauts exactly what to look for and precisely where to look for it once a crewed landing near the South Pole actually does take place. As one report covering the research put it directly, this new work suggests that material blasted up from deep inside the moon may still lie in parts of the South Polar region, areas that are currently under active consideration for Artemis exploration, meaning the specific rocks capable of finally answering some of the most fundamental remaining questions about the moon's early interior and formation history may already be sitting, quite literally, within walking distance of where NASA's astronauts are currently planning to land. There's a broader scientific significance to this kind of discovery that extends well beyond simply understanding the moon's own history in isolation. Because the moon is believed to have formed from debris created during a massive collision between the early Earth and a Mars-sized body, roughly 5 billion years ago, understanding the moon's own deep interior composition offers scientists valuable, otherwise inaccessible clues about the shared early history of both the moon and Earth during that same extraordinarily violent, formative period of our solar system's development. Earth's own deep interior, reshaped continuously over billions of years by plate tectonics, volcanic activity, and ongoing geological processes, has long since erased most of the direct physical evidence of what conditions were actually like during that same early period. The moon, lacking any of Earth's own active geological recycling processes, has preserved that record in a way our own planet simply hasn't been able to, making lunar mantle material, wherever it can actually be found and directly studied, a genuinely valuable, otherwise irreplaceable window into a shared chapter of planetary history that's been almost entirely erased here on Earth itself. This connects as well to complementary research already underway, using actual physical lunar samples rather than orbital data and modeling alone. In 2024, China's Chang'e 6 mission successfully returned the first ever physical samples collected directly from the moon's far side, material that has since been used by researchers studying, among other things, the long-standing puzzle of why the moon's near side, the hemisphere permanently facing Earth, and its far side look and behave so differently from one another geologically, differences that some researchers have directly connected to the same ancient colossal impact responsible for creating the South Pole Aitken Basin in the first place. Combining that kind of physical returned sample data with the detailed impact and gravity modeling described in these newer 2026 studies gives lunar scientists an increasingly complete, increasingly detailed picture of the moon's earliest history, built from multiple independent lines of evidence converging on a broadly consistent story. What all of this ultimately represents, brought together, is genuinely significant groundwork being laid specifically in service of NASA's broader Artemis program, even though it arrived before any astronaut has yet set foot near the South Pole itself. Scientists have used decades of accumulated orbital data, combined with sophisticated new computer modeling techniques, to identify precisely where, within the largest, oldest, most scientifically valuable impact structure in the entire solar system, astronauts might realistically expect to find material excavated directly from the moon's own deep interior, rock that formed under conditions no human being has ever been able to directly study, sitting exposed and waiting, quite literally, within the same handful of landing sites NASA has already identified as the leading candidates for humanity's return to the lunar surface. Somewhere within that vast, ancient, more than 2,000-kilometer-wide scar on the moon's far side, material from deep inside the moon itself is sitting exposed on the surface right now, has been sitting there for billions of years, ever since a massive object arrived from the north, struck the young moon at a shallow, glancing angle, and blasted pieces of its interior outward across the surrounding landscape. NASA's Artemis astronauts, whenever they finally do land near the lunar South Pole, may end up walking across some of that same material, picking it up and finally giving scientists the chance to study in a laboratory, with their own hands, rock that formed during the earliest, most violent chapter of the moon's entire 4.5 billion year history. If you want to follow how this research continues developing as NASA works toward finally landing astronauts near the lunar South Pole, that story is still very much unfolding right now. Subscribe if you'd like to keep following where it goes.